In the last batch of videos, we've been estimating the area under a curve by using what we've been calling Riemann sums, taking rectangles or maybe trapezoids and adding a bunch of those areas up because we know how to calculate those areas, and using that as an estimate for the area under the oddly shaped curve, which we don't have an area estimate for. And what I want to do is I want to take this activity that we've been doing and kind of translate it a little bit into the calculus stuff that we'll be talking about over the course of this unit and the next unit. So what we've got here is, so thinking of it like this, and this is going to use a little bit of Algebra 2 notation. We've got this sigma notation. And what we are calculating is the sum of, I'll say I equals 1 to n of rectangle sub I. All right, so we kind of have this shape, and we're using this as the estimate of our area. I'll have EA for estimated area. And let me break that down just one step further. I equals 1 to n. So what we've been doing to calculate the area of a rectangle, we'll stick with rectangles, is we have f of x sub I, where we're using some x value, either the left hand or the midpoint or the right hand, times delta x, which is the width of our common rectangle side. Okay, and so this has been kind of what we've been doing over the bunch of the last videos to calculate the estimated area. And so what we're going to say is we're going to say that the true area, notice that as n has gotten bigger and bigger, as we've gone from measuring 3 rectangles to 6 to 12, the estimates have gotten better and better. And you might think, and you would think correctly, that if we were to use 1,000,000 rectangles, we would have a really, really amazing estimate. In fact, when we've got really complicated functions, this is exactly how we would estimate that area, by asking the computer to do this for a whole bunch of rectangles, like 1,000,000 rectangles or 1,000,000,000 rectangles. And if you've got a programming bent, you might want to think about writing a program that would estimate the area of under this curve using 1,000,000 rectangles instead of just 12, and see how that estimate looks for the different techniques. But when we talk about the true area, we're going to switch over to a calculus notation. So this is going to be new. So instead of this letter, which is a capital sigma from the Greek alphabet, we're going to use this elongated S to talk about. Still, we're talking about sums. So we've got S for sigma, and now we've got this fancy big capital S shape. And we're going to say f of x, we're going to describe the function, because again, this is kind of the height of the function. And instead of thinking about the width of a rectangle, we're going to kind of imagine using an infinite number of rectangles. And those infinite number of rectangles have such a tiny, tiny width that it's essentially 0, but it's not quite 0. And so how do you quite describe that? And the way we do that in calculus for historical reasons, you will remember this from the first part, is that we would call that dx, a really, really small width of x times the height of x. Because remember, dy over dx means how much does a really, really small change in the y value of a function, of a graph of a function, change relative to the really, really, really small change in x. All right, and so just to give this some extra notation, when we've been measuring this curve, we've been measuring it with x equals 1 on the left-hand side and x equals 7 on the right-hand side. And so we would describe this as the integral from 1 to 7 of f of x dx. Okay? And in general, we would say the integral from a to b for different values of a and b. This is what is called a definite integral. Okay, so a definite integral is a number, okay, and it tells us the area under the curve. So if we've got a curve that looks like this talks about the area under this shape. And another thing to think about, I haven't mentioned it yet, but if a curve goes under the x-axis, we want to think about the area over here too, but this is going to be a negative area, whereas this is a positive area. Okay, so we'll see more of this as the weeks go on, but I just wanted to show you that negative integrals are something that definitely makes sense, but they talk about values of a function that go below the x-axis. All right, so this is the idea of Riemann sums and how they tie to definite integrals. We are going to talk not in the next section, but in the section after that of how we can absolutely correctly calculate the area under this curve we've been measuring for the last 5 or 6 videos. And so we'll have the actual true area to compare to all of the estimates that we've been doing. But we'll need to do one other thing first in the next week's lessons, which is talking about what we mean by an indefinite integral. And then we'll talk about how the indefinite integrals and definite integrals tie into each other, which is going to be a fascinating topic called the fundamental theorem of calculus. But for now, this is just what we need to know about definite integrals and how they tie to Riemann sums.